Now then, lambert W function. It's a fairly straightforward function to understand. All it is just the converse of x e to the x. So it's the solution to the equation f of x equals x e to the x. What is f to the minus 1 of x? That's about it really. It's just w of x. It cannot be represented in terms of elementary functions. That's why it has to be represented with as w of x. It's non-elementary, which means that it cannot no matter which operator you choose, you will not be able to represent it with that. So multiplication, addition, subtraction, exponentiation, you won't be able to represent it in terms of those. Or even hyper operations like tetration and pentation, you won't be able to represent it with those. In terms of those, I mean. Right. The first, well, this is problem 2. The first ones are all numerical. I don't fancy doing them. So the first of the second set of problems is quite straightforward. All you need to know is that when you get an invertible function, so it's a bijective function of x, and you invert it, and you plug the inverse of that function into the function, you will get your argument back. And this is important for future problems. And why is this the case? It's because when you invert a function, you are reflecting it about the line y equals x, and this essentially represents all the invariant points. All the points on the line y equals x are invariant when you reflect them about. You're reflecting them about the point it's at, so it's not going to move. So the first problem, you just know. Well, you know the inverse of the inverse of a function. It's just the function. So w of x times e to the w of x should give us our argument back, which is x. You just rearrange for the argument of the exponential. So this implies that e to the w of x equals x over w of x. Well, of course, w of x is non-zero in this case, which implies that then w of x is equal to the natural log of x over w of x. All I've done is just took a log of both sides. That's the problem done. It's fairly straightforward, that one. The next one, it's little bit of a quite a few lines. It's just a substitution. So I'm going to call x. I'm going to do a substitution of x equals y times e to the power of y. I'm going to plug that in there because I should get my argument back from the w of this. So this would equal 1 over n times the w of n times by y times e to the y to the power of n divided by w to the power of n minus 1 of y e to the y, which is equal to this is equal to y, and this is 1 over n times by w of n y to the n e to the y times n divided by, well, a y to the power of n minus 1, which is a y to the n divided by y, and when it's in the denominator you're essentially multiplying by y, because you're dividing by a negative power and you're just flipping the sign of that power. So negative of negative 1 is 1. And this simplifies to the y. This cancels. Y is non-zero. You got big problems when you divide by 0. N times by y times e to the power of y times n, which is equal w of that 1 over n, and it's pretty clear that this is just equal to n times y. The n cancels, n's non-zero. we end up with y equals y. So it must be true. And for the next problem, it's just a matter of another substitution. So we know if you input a function and if it's inverse, it's equivalent to finding what value of that function equates to it. So what you want is y times e to the power of y equals minus log x over x. And you could argue that it's fairly obvious that y equals 1 over x works for this. Oh, log of 1 over x. Because you've got the log of 1 over x times by e to the log of 1 over x. And this is equal to the log of 1 over x times by 1 over x, which is equal to minus log x divided by x. And that's exactly what we wanted to show. We end up with our argument that we wanted. And the next problem, we're simply just going to be utilizing this one right here, this statement right here. And this looks complicated, and it's really not. It looks intimidating, but a lot of problems in maths are like that. A lot of people are like that. They look intimidating, but they're really quite easy to deal with. So since we know this is the output of the Lambert product log, what you can do is plug it into the inverse to get the argument back. So w of x plus w of y times by e to the power of w of x plus w of y. This should equal the argument of the output, which is this, to the xy times by this. Well, this is our expected value. So we're expecting xy over w of x plus xy over w of y. And we need to expand and do a substitution. E to the w of x multiplied by e to the w of y plus w of y times by e to the w of x times by e to the w of y. And we can do a substitution for e to the w of x. All it is just e to the power of both sides of this statement here. So e to the w of x is equal to x over w of x. So we go ahead and substitute that. So we've got a w of x multiplied by an x and divided by a w of x multiplied by y divided by w of y plus w of y. I think you can see exactly why this is going to be true. Divide by w of wait, lost my train of thought. It'll be an x over w of x times by y over w of y. And for w of x and w of y, w of x equals w of y equals 0. This will not work. So let's sort of notate that better. They're both non-zero, of course, because you cannot cancel these if they're 0. 0 divided by 0 will be just undefined. You have to define them as limits of functions. But the thing is, they won't be equal to 0. There'll be limits tending to 0. So for as long as they're non-zero, it's fine. Just cancel these, and then we're left with xy over w of x. We'll just end up with this, so it's pretty clear. And that's about it, really. Those problems were quite simple.